Welcome to IAS Masterclass. This is Mr. Jose. In this Climatology Series, the first part, we are going to deal with the fundamentals of atmosphere, temperature, and pressure. Why is climatology very important for UPSC? For a couple of reasons. One, it's the most dynamic subject in physical geography. Now, what makes it the most dynamic subject of physical geography is it is always current. Courtesy, climate change. Now, in the last few years, if you look at the average, we've got somewhere like 3 to 5 questions asked in mains, that is General Studies Paper 1, 2 to 4 questions in prelims on an average, especially the climate change part. Now, why this subject is a little different from learning other subjects in geography is that there are no big jargons here, right? There are no big words and jargons. Once you get the fundamentals right, we are ready to go. It needs less time to prepare once the foundation is clear. Of course, it is valuable for future bureaucrats, their decision making. Okay, so let's start off. This is our syllabus for General Studies. Our optional syllabus is different. This is for General Studies, GS1. Basically, we start with the atmosphere, temperature and pressure changes in the troposphere, temperature inversion, pressure belts, planetary winds and local winds, jet streams, humidity, that is precipitation, clouds, types of rainfall, cyclones, where we deal with both tropical, extratropical, and temperate cyclones, climate classification, and of course, last but not the least, climate change. Let's start off. Climate and weather. Now, a lot of people interchange between climate and weather, isn't it? Now, it's simple. Weather is an expression which encapsulates the temperature, pressure, and humidity of a region at a certain point of time, whereas climate is long-term average weather conditions in an area. Long-term here means 50 years or so. Okay, there are 3 aspects of climate. Now, climatology means learning about climate means learning about 3 things, which are temperature, pressure, and humidity. Now, what is temperature? Temperature is an expression of the intensity of heat energy, right? So it is expressed in units, like we know that, right? In degrees Celsius, in Fahrenheit, even in Kelvin. Pressure. What is pressure? Pressure is force per unit area. Now here, when we are talking about the atmosphere, we are talking about the air pressure or the atmospheric pressure, wherein in a unit area, we look at the force exerted by a parcel of air. Now, a pressure, whether it's high or low, higher or lower, is actually dependent on the amount of air in that air parcel in a unit area. Okay, and humidity. Humidity is, of course, the amount of water vapor present in air. Now, we use 2 expressions of humidity. One is specific humidity, mostly, and relative humidity. Relative humidity is something that we are familiar with. See, when we say like 80% humidity, we mean 80% relative humidity. So what does that mean? That is, if a parcel of air has a capacity, right, to hold water vapor in it. Now, if of that capacity, 80% of that capacity is now full. Okay, so in order to make it saturated, you need 20% more. Okay, that is the idea of relative humidity. So, and this happens particularly at a certain temperature. Now, humidity per se is directly related to temperature. There are relations with humidity and pressure, but not so much. So, it is basically humidity and temperature. Okay, let's start off by learning about the basic things about our atmosphere. Our atmosphere is divided into various layers, as we know: troposphere, stratosphere, mesosphere, ionosphere, and exosphere. So all the climate activities are actually happening in the troposphere. So what is the height of troposphere? Around average height is, you can say, 12 kilometer. It varies from the equator to the poles. In the equator, the height of the troposphere would be the maximum. Why is that? It is because the convection currents in the equator are the maximum or the strongest. And the reason for that would be the direct sun's rays. Sun's rays, as we know, falls directly only over the tropics. The regions, extratropical regions, temperate regions, polar regions all receive indirect sun's rays. So troposphere, The height would be maximum at the equator and would be minimum at the poles. So above the troposphere, we have the stratosphere. Of course, stratosphere is, we know this is full of ozone. So where is this ozone concentrated? It is in the upper stratosphere. Ozone is there everywhere in all layers in the stratosphere, but it's more concentrated in the upper layers. That is between 35 and 50 kilometers. Mesosphere, of course, is the coolest layer of the atmosphere. Ionosphere, this layer is important in the sense, of course, as we see in the slide, here aurorae or the northern lights actually appear in this layer. The temperatures are very high and it destroys meteorites. Apart from that, there is a layer called Kennelly Heaviside layer. Kennelly, Kennelly Heaviside layer. Now this is around 150 kilometers above the surface. This layer is very important for radio communication. Then of course you have the outer layer of the atmosphere, which we call it as exosphere, that is beyond 500 kilometers. So these are the layers of atmosphere. All the climatic activities or meteorological activities happens in the troposphere only. So let's look at the troposphere. What are we basically interested in? We are looking at what happens in the troposphere in terms of the various aspects of climate. So let's start off with temperature. Now what happens to temperature? Temperature decreases with altitude in the troposphere. Or is it? Does it increase with altitude in the troposphere? Let's find out. Now what happens? What contributes to the temperature? It is of course insolation or incoming solar radiation. The incoming solar radiation is in the form of shortwave radiation. Now the atmosphere is not able to absorb heat from shortwave radiation. So most of this actually falls on the Earth's surface. The Earth's surface absorbs this heat and emits it back as terrestrial radiation. Now this terrestrial radiation is in the form of long wave radiation, which the aerosols in the atmosphere can absorb heat from. Hence the atmosphere is primarily heated from not directly from the sun's rays, incoming solar radiation, but from terrestrial radiation. That means what? That means layers or the bottom layers near to the surface of Earth will be warmer than the upper layers. Hence we can say temperature decreases in the troposphere with altitude. Decreases with altitude in the troposphere. There can be exceptions in this, all right? And these exceptions are what is called temperature inversions. We'll deal with temperature inversions in detail in our next video. Now, pressure also decreases with altitude in the troposphere. Okay, we'll deal with pressure also in detail. What is pressure? We already said pressure is force per unit area. Temperature at a place is dependent on many factors, which are altitude, which we have seen already, latitude. The latitude of a place determines the temperature by the fact that the sun's rays are direct only over the tropics, and all the extratropical and polar regions are fed with indirect sun's rays. So naturally, the temperatures would be relatively higher in the tropics. So the latitude plays an important part. Now, continentality of a region. That means, what is this region we are talking about? Is this an interior of a continent? Is this a coastal region? Is this an oceanic region? Or is it part of a large water body? In an ocean, there are hardly any changes in temperature over the day. You find that the diurnal range of temperature over ocean surfaces is hardly around 0.5 degrees Celsius or even lesser. Whereas the land gets heated up and cooled down faster over a day. So it depends on where that place is, whether it's part of an ocean or part of a land, is part of is a interior of continent, or is it a coastal region. Ocean currents and winds also contribute to the temperature on a big level. Wherever you find cold ocean currents or cold winds blowing, those coastal regions are characterized by moderate temperatures as compared to regions in the interior of continents, which would be covered with seasonal high and low of temperatures. Slope and aspect of slope. Now what is slope? Slope is a gradient. Let's take an example of the Alps or the Himalayas. Both these mountain ranges are oriented from east to west. or west to east, as you can call it. Since the sun's rays are also oriented in these directions, these slopes, that is the southern slopes of both the Alps as well as Himalayas, will receive direct sunlight. That means the temperatures would be relatively higher there as compared to the northern slopes of these mountain ranges. Aspect of a slope is actually the orientation of that slope vis-a-vis the sun's rays. Natural vegetation and soil also has a bearing on the temperature. Let us take the example of Amazon rainforest. Amazon rainforest, as we know, is a rainforest which is actually having a complete foliage. You can say that. That means what? It blocks most of the sun's rays. At the surface, Earth's surface receives very less of sun's rays because of that thick canopy. That means the temperatures would be relatively cooler as compared to a place in the same latitude which is relatively plain and is a desert. So all these factors contribute to temperature of a region. Okay, let's look at this slide where we see in that graph that the pressure decreases as we go up higher in altitude. This always happens. There are no exceptions here. So what is the reason behind this? The reason is that the air column thins out as we move upwards. The air column thins out. That means the force which will be acting over a certain area, in an unit area, will become progressively lesser as we go upwards. The reason is air gets thinner. Now imagine, we know that mountaineers always use oxygen mask when they climb mountains, right? The reason is this, because it's thin air. Okay. Pressure always, there is a gradient which is created. That is, there will always be a high pressure region surrounded by a low pressure region, or maybe there will be a high pressure region and a lower pressure region surrounded by a higher pressure region. All right. So that's how it goes. Okay. Now what happens when insolation falls on the Earth's surface? We know air gets heated up, Earth gives out terrestrial radiation, and air gets heated up. Now what happens to this air? Air, when it gets warmer, it becomes lighter, and as it gets lighter, it becomes less denser and it rises. Okay, imagine an inflated balloon. Okay, it rises, no? So that is because air is getting warmer in it. So it is warmer air in it. So it rises. Air, when it rises, it actually creates convection currents. Convection, as we know, is one of the three processes of heat transfer. The other two are conduction and radiation. Okay, now when convection current happens, the warmer air rises up, cools down as it increases in altitude. Then as it becomes denser, it actually sinks. It may or may not sink at that same location. That is driven by other factors. For example, centrifugal force, which will come later. Okay, now let us understand pressure belts. What are pressure belts per se? Pressure belts are areas where there are definite conditions of pressure, which are seasonal, of course. We say that the pressure in that area, in that region, or in that belt would be lower or higher as compared to another region, which is in the neighborhood. Now, when you say the neighborhood, we are not referring to like 2 kilometers or 5 kilometers. We are looking in terms of latitudes here. Okay, so there are 7 pressure belts. Now let's see how these pressure belts develop. Okay, now the first pressure belt is the equatorial low pressure belt. Equatorial low pressure belt, no marks for guessing why it is low pressure at the equator. Why is that? It is because of the sun's rays. Sun's rays are always direct, so warmer air always rises. Warmer air rises means there is low pressure. Now what happens to this air as it rises? It progressively cools down. Now as it cools down, it becomes denser also. It attempts to sink. But what happens? Since the Earth is not a stationary body, it is rotating. And there is something called as centrifugal force. Now what is centrifugal force? Centrifugal force is any rotating body, if you say. Okay, there is always a force which attempts to take that body away from that rotating frame. For example, if you look at a fan, a running fan, and if God forbid that fan falls down, if you are just beneath that fan, you are almost safe, right? because that fan will be actually going into any of the sides. That is because of centrifugal force. Here, in the case of Earth, the centrifugal force is maximum at the equator. Okay, what is the shape of the Earth? It's a geoid, right? It's like a flattened orange. Now, that bulge at the equator and flattening at the poles. That bulge at the equator means it is due to high centrifugal force. And the centrifugal force, of course, would be minimum at the poles, at the polar region. Centripetal attractive force would be maximum at the poles and minimum at the equator. Okay. Now, what has happened to our recent air in the equatorial low pressure belt? The recent air attempts to come down, but it is swept towards the poles on either side by centrifugal force. Since this air is actually cooler and denser, it cannot actually move right till the poles. So what happens is, most of this air will actually sink somewhere around 30° north and south latitudes. Now, in 30° north and south latitudes, we'll have regions of descending air. Descending air actually increases the pressure in those regions. Hence, we have two more pressure belts, subtropical high pressure belts, both in the northern hemisphere, one in the northern hemisphere and one in the southern hemisphere. So most of the air from the equator which has risen actually has come down, but the rest of the air actually goes towards the poles. As we said earlier, the centripetal attractive force at the poles are the maximum, and this attractive force causes that air which is near to that subtropical region to go there into the poles, which gets absorbed and it descends at the polar region. It also induces air from the region around 65° latitude, now both north and south latitudes. This air from the 65° north and south latitudes at the Earth's surface rises in order to descend in the polar region. Now that creates four pressure belts, which are, as we see in this diagram, you have the subtropical high pressure belt, then there is a subpolar low pressure belt, then the polar high pressure belt. So in all this, we can say there are 7 pressure belts. One equatorial low pressure belt, which we also call as doldrums, subtropical high pressure belt, which we call it as host latitudes, which is there mostly in both the hemispheres. Subpolar low pressure belt, again north and south, around 65° north and south, and polar high pressure belt at around 90° north and south. Okay, we have one thing to deal with, temperature inversion, which we will actually deal with in the next video. In the next video, we'll deal with winds also, ITCZ, which is the intertropical convergence zone, dynamic theory of monsoon, which is a product of shifting of pressure belts, and also jet streams. Video. Keep watching IAS Masterclass. I'm signing off. Thank you. Bye-bye.